Welcome back. In this video, we're going to look at example problems involving Macaulay and modified convexity. Let's get to it. All right, so here's our first example. Chris has the following cash flows: $40,000 in 2 years, $25,000 in 3 years, and $100,000 in 4 years. Given an effective annual interest rate of 7%, find the Macaulay convexity and modified convexity of Chris's cash flows. All right, so this is the most basic type of problem that you will see when you want to calculate Macaulay or modified convexity. We are given a series of cash flows for a particular account, in this case Chris's account, and we want to find the Macaulay convexity and modified convexity for those cash flows. And so the first thing that we should do here to organize the information that we've been given is draw a timeline and label where these different cash flows are taking place. All right, now from the information that we've been given, I can see that the farthest out that we will need to label is 4 years. Chris doesn't have any other cash flows past the 4-year mark, so that's where I'm going to stop in drawing my timeline here. So we'll draw t equals 0 right here, and then I'll make our timeline about this long. And then here's t equals 1, t equals 2, t equals 3, and t equals 4. All right, and then I'll label them. Time equals 0, time equals 1, time equals 2, time equals 3, and time equals 4. All right, so the first cash flow that we know about is this $40,000 in 2 years. So if we're starting at time equals 0, 2 years later would be at time equals 2. So we have $40,000 at time equals 2. Then the next cash flow is $25,000 in 3 years. So if we're starting at time equals 0, 1, 2, 3, takes us to time equals 3. So we have $25,000 at time equals 3. And then the last cash flow that we know about is this $100,000 in 4 years. And so once again, if we're starting at time equals 0, 1, 2, 3, 4, takes us to time equals 4. So right here we have a cash flow of $100,000. All right, now the only other thing that we're told about in this problem is that Chris has an effective annual interest rate of 7%. And so I equals 7%, which in decimal form is 0.07. All right, so now we have a timeline of all the cash flows that we're working with in this problem, and we have identified the interest rate. And so now we're ready to find the Macaulay convexity and modified convexity for these cash flows. And we're going to start with the Macaulay convexity. Whenever you have to find both the Macaulay and the modified convexity, I would recommend that you start with the Macaulay convexity. And so the Macaulay convexity can be calculated using the following formula. The Macaulay convexity, or the MacC, is equal to this expression. We'll have the sum from t equals 1 to n of t squared times c sub t times v to the power of t divided by the sum from t equals 1 to n of c sub t times v to the power of t. All right, and so essentially what we're doing here in the numerator is we're summing up the amount of our cash flows at each individual time and multiplying them by the time at which they are made, but squaring that time, and then multiplying by the appropriate present value factor to take it back to time equals 0. And then we're dividing by the present value of all of the payments, or all of the cash flows. So in the denominator, we have the present value of the cash flows, and then in the numerator, we would also have the present value of the cash flows, except each term is being multiplied by t squared, where t represents the time where each payment is made. All right, and even though the index in this summation in the numerator and denominator starts at t equals 1, we don't have to worry about including a term for time equals 1, since the cash flow at that time would be 0, right? There's no cash flow at time equals 1. So if we were to write out that first term, we would have 1 squared times a cash flow of 0, right? C sub t represents the amount of your cash flow, and so if there's no cash flow at a particular moment in time, it's just 0, and that whole term would be gone. All right, but here's what we're going to have in this case. The Macaulay convexity will be equal to each of our cash flows multiplied by the time at which they are made, but that time will be squared, and then we're going to multiply them by the present value factor that would bring those payments back to t equals 0. All right, so let's start with our first cash flow of $40,000 at t equals 2. We'll have 2 squared times 40,000 times v squared. All right, so this $40,000 was made at time 2, so we have that value of t right here, but square it, 2 squared, multiply it by the amount of the cash flow, and then multiply it by the present value factor squared, which will take that cash flow back 2 years to time equals 0, where the present value is valued. All right, so that takes care of the first cash flow. Now let's look at the second one, which is $25,000 at time equals 3. We will add 3 squared times 25,000 times v cubed. All right, so that cash flow of $25,000 was made at time equals 3, so we have that value of t squared multiplied by 25,000, the amount of the cash flow, and then multiplied by the present value factor cubed, which will take it back 3 years to time equals 0. All right, and then finally, let's work with our last cash flow, which is this $100,000 at time equals 4. So we will have plus 4 squared times 100,000 times v to the power of 4. Now I kind of had to smush that in there, but this is 4 squared times 100,000 times the present value factor to the power of 4. All right, so that will take that payment back 1, 2, 3, 4 years, and we're multiplying it by the year at which it was made, which is t equals 4, and we're squaring that value of t. Okay, so that's the numerator of our calculation, and then that will be divided by the present value of our cash flows. And so that's just going to be the same as the numerator, except we're not going to be multiplying by the times squared. So we'll have 40,000 times v squared plus 25,000 v cubed plus 100,000 v to the power of 4. Okay, and that's it. This is the calculation for the Macaulay convexity of these cash flows. And so what you can do is plug this expression into your calculator to get the value of the Macaulay convexity. Just remember that we are using an interest rate of 7% or 0.07. And so just remember that each present value factor is equal to 1 divided by 1 plus I to the power of t, which means that they are equal to 1 divided by 1.07 to the power of t. All right, so whatever the power of those present value factors are determines the power of t in this expression. All right, so if you use this for each of those present value factors and plug all this into your calculator, you will find that the Macaulay convexity is equal to 11.7298 and some more decimals. So that is the first part of this example. We wanted to find the Macaulay convexity and the modified convexity. So now we need to work on the modified convexity next. And so in order to calculate the modified convexity, we will need to remember the formulas associated with the modified convexity. All right, and so one of the formulas for modified convexity is this. The modified convexity is equal to the second derivative of the present value function divided by the present value function. All right, and the present value function would just be equal to the present value of our cash flows, but where the present value factors would be written out explicitly in terms of I. So essentially the present value function would just be the denominator of this calculation right here for the Macaulay convexity. This is the present value of these cash flows, but we would just rewrite what v is equal to, which is 1 divided by 1 plus I to the power of t, or whatever the power of the present value factor is. All right, so we could go about that and then take the derivative of that 2 times and evaluate both of those functions at the interest rate to find the modified convexity. However, there is an easier way to go about this for this particular problem. In fact, I would actually recommend what we're going to do instead over this method in most scenarios. I think that this way that I'm going to show you is a much easier approach to calculating the modified convexity. Instead of using this definition, what we can do is make use of another formula for the modified convexity. I showed why this is true in my lesson video, but the modified convexity is equal to the Macaulay duration plus the Macaulay convexity times the present value factor squared. All right, now the reason why this is helpful is because we already calculated the Macaulay convexity, and the Macaulay duration is a very similar calculation to the Macaulay convexity. Right, because the Macaulay duration can be calculated using this formula, and this formula is almost exactly the same as what we use to calculate the Macaulay convexity, except that that t that we're multiplying by the cash flows and the present value factors is not squared. It's just t to the first power. So this calculation right here that we use to calculate the Macaulay convexity, all we have to do to find the Macaulay duration that we can then use for this calculation to find the modified convexity is just not square 2, 3, and 4. If we just remove that exponent of 2 to each of those constants, we will then have the appropriate calculation for the Macaulay duration. So here's what we'll have. The Macaulay duration will be equal to 2 times 40,000 times v squared plus 3 times 25,000 times v cubed plus 4 times 100,000 times v to the fourth. And then that is divided by the present value of those cash flows, which is 40,000 v squared plus 25,000 v cubed plus 100,000 v to the power of 4. So this is the calculation for the Macaulay duration. It's pretty much the same thing we did for the Macaulay convexity, except 2, 3, and 4 are no longer squared. They are just raised to the first power. And so if you plug all this into your calculator, just remember to replace v, or the present value factor, with what it's equal to in terms of I. Once again, remember that v to the power of t in this example will be 1 divided by 1.07 to the power of t. And so if you remember that and plug this into your calculator, you will find that the Macaulay duration is equal to 3.314 and some more decimals. All right, now I probably should have mentioned this earlier, but make sure to save this value and this value for the Macaulay convexity in your calculator, and then use them again to calculate the modified convexity. It's probably for the best that you don't round these numbers off when you use them in this calculation right here. Try to use the exact values or as many decimals as you can when you go to calculate the modified convexity so that it is as accurate as it can be. All right, I just shortened them here so that I can fit them on the screen, but obviously there are way more decimals to each of these answers that we should take into account. All right, but now that we have the Macaulay convexity and the Macaulay duration, we can use those two calculations to find the modified convexity. All right, so here's what we'll have. The modified convexity is equal to the Macaulay duration, which is 3.314 and some more decimals, and that will be added to the Macaulay convexity, which is 11.7298 and some more decimals, and that will be multiplied by the present value factor squared. Now, if you wanted to, you could rewrite that to be 1 divided by 1.07 squared. Either way, if you plug this into your calculator, it will give you that the modified convexity is equal to 13.14 and some more decimals. That is the modified convexity for these cash flows. All right, and so now we've completed this problem. We found the Macaulay convexity and the modified convexity for Chris's cash flows that we have detailed right here in this timeline. Okay, that's it for this example, but let's take a look at one more example for this video. All right, so here's our second example. We have that a company has incoming assets of $7,000 in 1 year, $5,000 in 3 years, and $9,000 in 5 years. The company also has liabilities due of $6,000 in 2 years and $13,000 in 4 years. Given that both the assets and liabilities for the company are valued using an effective annual interest rate of 5%, determine whether the assets or liabilities have a larger Macaulay convexity. All right, so in this problem, we're going to be calculating two different Macaulay convexities. We're going to be calculating the MacC for a set of cash flows that are labeled as assets, and we're going to calculate the MacC for a set of cash flows labeled as liabilities. Now, you're actually going to learn more about asset liability management in the next couple lessons, but for this example, all we have to do is make sure that we label each of these cash flows as an asset or a liability so that we use the appropriate cash flows in our calculation for the Macaulay convexity. All right, we don't really need to know more than that for this example. Okay, but we do have a lot of cash flows to deal with here, right? We have 1, 2, 3, 4, 5. So let's draw out a timeline and let's organize everything so that we know what's an asset, what's a liability, and how much of each and at what time. And for our timeline, I see that the biggest amount of years in the future that we will need to look at is 5 years. Just by looking quickly at each of our cash flows, the farthest in the future that any of them are incoming or leaving the account is in 5 years. So I'll make sure to label out to year 5 in our timeline. So we'll start with time equals 0, and then draw a big line here. This will be time equals 1, time equals 2, time equals 3, time equals 4, and time equals 5. All right, and now let's label them. T equals 0, T equals 1, T equals 2, T equals 3, t equals 4, and t equals 5. Now I'm going to label all of the assets in one row along this timeline, and then I'm going to label all of the liabilities in another row. That way we can distinguish between them. And so let's start with the assets. We are told that the company has incoming assets of $7,000 in 1 year. So if we're starting at t equals 0, that will be at time equals 1. So we have $7,000 right there. Then they have $5,000 in 3 years. So time equals 3 is right here. So we'll have 5,000. And then $9,000 in 5 years. So at time equals 5, we will have $9,000. Now for the liabilities, the company has liabilities due, which means that they're payments leaving the account. They're making payments of these amounts. These aren't incoming payments. These are payments that are leaving. But once again, you don't really need to know that per se for this example. But the liabilities due are of $6,000 in 2 years. So that will be at t equals 2. We'll have 6,000 and 13,000 in 4 years. So at t equals 4, we will have 13,000. All right, and then one more thing that we want to make a note of here is that both the assets and liabilities are valued using an effective annual interest rate of 5%. So that means that I is equal to 5%, which in decimal form is 0.05. Okay, so now that we have identified our interest rate and we have drawn out a timeline that shows all of the assets and liabilities, let's work on calculating the Macaulay convexity for each of these sets of cash flows. We're going to treat the assets and liabilities as two separate sets of cash flows, right? We want to determine whether the assets or liabilities have a larger Macaulay convexity, so we're going to need to calculate the Macaulay convexity for both of these sets and see which one is bigger. Okay, and so remember, to calculate the Macaulay convexity for a set of cash flows, we will use this formula. We'll take the present value of each of the cash flows, multiply them by the time at which they are made, but square that time and then divide that by the present value of the cash flows. All right, that's what this tells us. Okay, now to get a little bit more space to calculate each of these convexities, I'm going to make this timeline a little bit smaller. And so here's what we're going to have. The Macaulay convexity of the assets will be equal to our cash flow at time 1, but we're going to square that time. And the amount of that cash flow is 7,000, and then we're going to take that back 1 year, so that it is valued at t equals 0. Then we'll add that to our next cash flow, which is made at time equals 3. So we'll have 3 squared times 5,000 times v cubed, right? That $5,000 is made at time equals 3, so we need to bring it back 1, 2, 3 years to the present. All right, so the present value factor is cubed. And then finally, we have a cash flow of $9,000 made at year 5, or time equals 5. So we'll have plus 5 squared times 9,000 times v to the power of 5. All right, the present value factor is to the power of 5 because we need to bring this payment back 1, 2, 3, 4, 5 years to be valued at t equals 0. Okay, and then we'll divide that by the present value of those cash flows, which is just the same thing that we have up here, but without each of the times squared. So we'll have 7,000 times v plus 5,000 v cubed plus 9,000 v to the power of 5. All right, so that's going to represent the Macaulay convexity of the assets. Now let's set up the Macaulay convexity for the liabilities. That's going to be equal to the time of the first liability cash flow, which is t equals 2. We'll have that squared. So we'll have 2 squared times the amount of that cash flow, or of that liability, which is 6,000. And that will be multiplied by v squared. That will bring that payment back 2 years to the present. And then we'll add that to the time of the second cash flow, which is t equals 4. So we'll have 4 squared times the amount of that cash flow, which is 13,000. And then we'll multiply that by the present value factor to the power of 4, which will bring it 1, 2, 3, 4 years back to the present. All right, and then we'll divide by the present value of the two cash flows, which will be 6,000 v squared plus 13,000 v to the power of 4. Okay, so now we have written out the calculations for the Macaulay convexity of the assets and the Macaulay convexity of the liabilities. Now all we have to do is see which one of these values is bigger. All right, and so remember, when you calculate these two amounts, that the interest rate is 0.05, it's 5%. So our present value factors of v to the power of t will be equal to 1 divided by 1 plus I, which will be 1.05 to the power of t. All right, so make sure to use that for each of those present value factors in these two calculations. But if you have everything set up like I do right here, and you plug it into your calculator, here's what you'll find. The Macaulay convexity of the assets is going to be equal to 12.298 and some more decimals, and the Macaulay convexity of the liabilities will be equal to 11.953 and some more decimals. And so clearly we can see that 12.298 is bigger than 11.953, so the Macaulay convexity of the assets is bigger than the Macaulay convexity of the liabilities. And that's all we needed to determine in this problem. We wanted to determine whether the assets or liabilities have a larger Macaulay convexity. So here's our final answer. The Macaulay convexity for the assets is greater than the Macaulay convexity for the liabilities. That is the answer to this problem. Okay, and so with that, that is the end of this example, and this is the end of this video. However, if you want to see some more examples involving Macaulay and modified convexity, I do have a couple more available on my membership site. And so if you're interested in seeing some more examples on this topic and the other topics that I've covered as well, I'd encourage you to look into joining the membership site because you might find those other examples to be helpful as well. Not to mention that the membership site also has dark mode versions of all of my videos here on YouTube, meaning that there's a black background and white writing. And so if that sounds like something that might be interesting to you, feel free to check that out once again. I'd encourage you to join. But with that, that's all I had for this video. So if you have any questions, feel free to leave those in the comments. But if you don't have any questions, this is all I had for now. So I will see you next time.